right, at index 5. For the second example, at the second row, or row index 1, we are interested in the probability assigned to index 13. At the second example, we also have 13. At the third row, we want 1. And at the last row, which is 4, we want 0. So these are the probabilities we're interested in, right? And you can see that they're not amazing, as we saw above. So these are the probabilities we want, but we want like a more efficient way to access these probabilities, not just listing them out in a tuple like this. So it turns out that the way to do this in PyTorch, one of the ways at least, is we can basically pass in all of these, sorry about that, all of these integers in vectors. So these ones, you see how they're just 0, 1, 2, 3, 4. We can actually create that using torch.arrange of 5. 0, 1, 2, 3, 4. So we can index here with torch.arrange of 5. And here we index with y's. And you see that that gives us exactly these numbers. So that plucks out the probabilities that the neural network assigns to the correct next character. Now we take those probabilities and we actually look at the log probability. So we want to dot log, and then we want to just average that up. So take the mean of all of that, and then it's the negative average log likelihood that is the loss. So the loss here is 3.7 something, and you see that this loss, 3.76 is exactly as we've obtained before, but this is a vectorized form of that expression. So we get the same loss. And the same loss we can consider sort of as part of this forward pass, and we've achieved here now loss. Okay, so we made our way all the way to loss. We defined the forward pass, we forwarded the network and the loss. Now we're ready to do the backward pass. So backward pass, we want to first make sure that all the gradients are reset, so they're at 0. Now in PyTorch, you can set the gradients to be 0, but you can also just set it to none. And setting it to none is more efficient. And PyTorch will interpret none as like a lack of a gradient and is the same as zeros. So this is a way to set to 0, the gradient. And now we do loss dot backward. Before we do loss dot backward, we need one more thing. If you remember from micrograd, PyTorch actually requires that we pass in requires grad is true, so that we tell
Where is my weight? second later, I forgot. I will do the cleanup of the code after some time. It has become pretty messier. Where I was, it was here. I calculated the weights again. For the time being, I will remove this one. I calculate the loss backward, and weights and everything.
PyTorch that we are interested in calculating the gradient, then set to none and loss.backward. Now, something magical happened when loss.backward was run. Because PyTorch, just like micrograd, when we did the forward pass here, it keeps track of all the operations under the hood. It builds a full computational graph. Just like the graphs we produced in micrograd, those graphs exist inside PyTorch. And so it knows all the dependencies and all the mathematical operations of everything. And when you then calculate the loss, we can call a dot backward on it. And dot backward then fills in the gradients of all the intermediates all the way back to W's, which are the parameters of our neural net. So now we can do W.grad, and we see that it has structure. There's stuff inside it. And these gradients, every single element here, so W.shape is 27 by 27. W.grad's shape is the same, 27 by 27. And every element of W.grad is telling us.
Oh, okay, I got it. Okay, sorry. These are the number of elements that it has. Okay.
The influence of that weight on the loss function. So for example, this number all the way here, if this element, the 0, 0 element of W, because the gradient is positive, is telling us that this has a positive influence on the loss, slightly nudging W, slightly taking W, 0, 0, and adding a small h to it would increase the loss mildly, because this gradient is positive. Some of these gradients are also negative. So that's telling us about the gradient information, and we can use this gradient information to update the weights of this neural network. So let's now do the update. It's going to be very similar to what we had in micrograd. We need no loop over all the parameters because we only have one parameter, tensor, and that is W. So we simply do W.data plus equals, we can actually copy this almost exactly, negative 0.1 times W.grad. And that would be the update to the tensor. So that updates the tensor. And because the tensor is updated, we would expect that now the loss should decrease. So here, if I print loss that item, it was 3.76, right? So we've updated the W here. So if I recalculate forward pass, loss now should be slightly lower. So 3.76 goes to 3.74. And then we can again set grad to none and backward, update, and now the parameters changed again. So if we recalculate the forward pass, we expect a lower loss again, 3.72.
If we do it like 5 times, W is already calculated and everything, so we see the error. Now what we can do is so we can use the P and N X. This is one way of doing it. There's a neural network way of doing it. Now we'll do the microgrid way of doing it using all of the function. Well, it makes sense also not working. Microgrid. But let's go through this video and see.
Okay, and this is again we're now doing gradient descent. And when we achieve a low loss, that will mean that the network is assigning high probabilities to the correct next characters. Okay, so I rearranged everything and I put it all together from scratch. So here is where we construct our dataset of bigrams. You see that we are still iterating only over the first word, Emma. I'm going to change that in a second. I added a number that counts the number of elements in X's so that we explicitly see that the number of examples is 5.
Okay. This is helpful. What usually prevents it? Okay, printing. That's the problem. Where it went. So we have 67 such tuples. Okay, this is where we are doing the encoding of all of this, and it should be defined one. So there is something like initialization, and this is encoding. Okay, all the encoding is done. Now we are doing gradient descent. So we are doing forward pass and everything, and taking weights and everything, going through it. Here we can specify it as num now and everything, and that's how the error looks like. And that is the word prediction that we have. And the same thing, right, I want to replicate with microgrid, but let me see what else he's doing.
Because currently we're just working with Emma, and there's 5 bigrams there. Descent of forward pass, backward pass, and an update. And so running these 2 cells, initialization and gradient descent, gives us some improvement on the loss function. But now I want to use all the words. And there's not 5, but 228,000 bigrams now. However, this should require no modification whatsoever. Everything should just run, because all the code we wrote doesn't care if there's 5 bigrams or 228,000 bigrams, and with everything should just work. So you see that this will just run. But now we are optimizing over the entire training set of all the bigrams. And you see now that we are decreasing very slightly. So actually we can probably afford a larger learning rate. We can probably afford even larger learning rate. Even 50 seems to work on this very, very simple example, right? So let me reinitialize and let's run 100 iterations. See what happens. Okay. We seem to be coming up to some pretty good losses here. 2.47. Let me run 100 more. What is the number that we expect, by the way, in the loss? We expect to get something around what we had originally, actually. So all the way back, if you remember, in the beginning of this video, when we optimized just by counting, our loss was roughly 2.47 after we added smoothing. But before smoothing, we had roughly 2.45 likelihood. Loss. And so that's actually roughly the vicinity of what we expect to achieve. But before we achieved it by counting, and here we are achieving roughly the same result, but with gradient-based optimization. So we come to about 2.462.
So by count method, this also I will do a bit of cleaning here. This is one thing. And then iterating out one thing. Counting. Then we have to calculating the probability. Just check this is fine. Yeah, this is fine. And also here, let's use the same generator that we used there now. Rather than defining a new generator altogether. Okay. Okay. The loss that we got 1.21 using this method. Okay. So if we just roughly take the probabilities based on the count and the negative log likelihood, right, it directly comes to 1.21. There's no learning or anything like that. We just cleanly calculate which tuples are coming more, and when we are doing this prediction, just taking into account how many of them are coming. But here when we're doing the same using the it has to change it more. Mm, reduced a bit to 1.32 or something like that. And set and what we want to predict. So I think it takes this one there. So this is what we get if we do using neural nets.
2.45, etc. And that makes sense because fundamentally we're not taking in any additional information. We're still just taking in the previous character and trying to predict the next one, but instead of doing it explicitly by counting and normalizing, we are doing it with gradient-based learning. And it just so happens that the explicit approach happens to very well optimize the loss function without any need for gradient-based optimization, because the setup for Bigram language models is so straightforward, it's so simple, we can just afford to estimate those probabilities directly and maintain them in a table. But the gradient-based approach is significantly more flexible. So we've actually gained a lot because what we can do now is we can expand this approach and complexify the neural net. So currently we're just taking a single character and feeding into a neural net, and the neural net is extremely simple. But we're about to iterate on this substantially. We're going to be taking multiple previous characters, and we're going to be feeding them into increasingly more complex neural nets. But fundamentally, the output of the neural net will always just be logits. And those logits will go through the exact same transformation. We are going to take them through a softmax, calculate the loss function and the negative log likelihood, and do gradient-based optimization. And so actually, as we complexify the neural nets and work all the way up to transformers, none of this will really fundamentally change. None of this will fundamentally change. The only thing that will change is the way we do the forward pass, where we take in some previous characters and calculate logits for the next character in the sequence. That will become more complex, and but we'll use the same machinery to optimize it. And it's not obvious how we would have extended this bigram approach into the case where there are many more characters at the input, because eventually these tables would get way too large because there's way too many combinations of what previous characters could be. If you only have one previous character, we can just keep everything in a table that counts. But if you have the last 10 characters that are input, we can't actually keep everything in a table anymore. So this is fundamentally an unscalable approach, and the neural network approach is significantly more scalable, and it's something that actually we can improve on over time. So that's where we will be digging next. I wanted to point out two more things. Number one, I want you to notice that this xenc here, this is made up of one-hot vectors. And then those one-hot vectors are multiplied by this W matrix. And we think of this as multiple neurons being forwarded in a fully connected manner. But actually what's happening here is that, for example, if you have a one-hot vector here that has a 1 at, say, the 5th dimension, then because of the way the matrix multiplication works, multiplying that one-hot vector with W actually ends up plucking out the 5th row of W. Logits would become just the 5th row of W. And that's because of the way the matrix multiplication works. So that's actually what ends up happening. But that's actually exactly what happened before. Because remember, all the way up here, we have a bigram. We took the first character, and then that first character indexed into a row of this array here. And that row gave us the probability distribution for the next character. So the first character was used as a lookup into a matrix here to get the probability distribution. Well, that's actually exactly what's happening here. Because we're taking the index, we're encoding it as one hot and multiplying it by W. So logits literally becomes the appropriate row of W. And that gets, just as before, exponentiated to create the counts, and then normalized and becomes probability. So this W here is literally the same as this array here. But W, remember, is the log counts, not the counts. So it's more precise to say that W exponentiated, W.x, is this array. But this array was filled in by counting and by basically populating the counts of bigrams, whereas in the gradient-based framework, we initialize it randomly, and then we let the loss guide us to arrive at the exact same array. So this array exactly here is basically the array W at the end of optimization, except that we arrived at it piece by piece by following the loss. And that's why we also obtain the same loss function at the end. And the second note is, if I come here, remember the smoothing where we added fake counts to our counts in order to smooth out and make more uniform the distributions of these probabilities. And that prevented us from assigning 0 probability to any one bigram. Now, if I increase the count here, what's happening to the probability? As I increase the count, probability becomes more and more uniform, right? Because these counts go only up to like 900 or whatever. So if I'm adding plus a million to every single number here, you can see how the row and its probability then when we divide is just going to become more and more close to exactly even probability, uniform distribution. It turns out that the gradient-based framework has an equivalent to smoothing. In particular, think through these W's here, which we initialize randomly. We could also think about initializing W's to be 0. If all the entries of W are 0, then you'll see that logits will become all 0, and then exponentiating those logits becomes all 1, and then the probabilities turn out to be exactly uniform. So basically when W's are all equal to each other, or say especially 0, then the probabilities come out completely uniform. So trying to incentivize W to be near 0 is basically equivalent to label smoothing. And the more you incentivize that in a loss function, the more smooth distribution you're going to achieve. So this brings us to something that's called regularization, where we can actually augment the loss function to have a small component that we call a regularization loss. In particular, what we're going to do is we can take W, and we can, for example, square all of its entries, and then we can, sorry about that. We can take all the entries of W and we can sum them. And because we're squaring, there will be no signs anymore. Negatives and positives all get squashed to be positive numbers. And then the way this works is you achieve 0 loss if W is exactly or 0. But if W has non-zero numbers, you accumulate loss.
About that later. This was one other way of the neural network way of achieving that. My intention next was to do it using the micrograd class that we created, and that's where I was defining it. So I just wanted to use that to reach, sorry, to reach at the same result, I would say. So I'm defining, I'm trying to do it from scratch, trying to define my own node function. I think sometime later I can go through the whole code that I have written. Let us give this name as micrograd. It goes through micrograd. I'm doing the same set of operation, just that using the micrograd class and defining each of them. I myself encode encode piece of code also I need to take, sorry. Encode, where is it? Yeah. So I'm just trying to take the same thing and work it out here. So this is one of the initialization pieces. This is where we do the encoding. Sorry. Means I could have tried to define this from scratch, but yeah. I've just used it as part of it. Majorly, I want to do the dot product and how that we backpropagate and everything using there. Right? So just to check right how the encoding looks like. So encoding is this way. So we are taking each of these in here. Returning the dot product of the whole vector. The only thing is she each of them is tens. Don't think this is required. Okay, number of elements. Don't worry, I will take this through. First, let me figure this out. So we got the number of elements in here. What will this work? No, this won't work, right? Previous. How I was doing encoding before this. Deleted that code, I think. Just give me a moment. So here, X encoding dot toolless. Just to make my life a bit easier, right? The tensor I do. Let's do. This is really a hacky way of doing things, I believe, but just I wanted to reach the solution process. So this is one out, and then we can. This is no, if you do, it's an array of sorry. Now it has become a normal list here. This is a length, sorry. So we get for each of those 68, 67 bigrams that we had, right? The one hot encoding for each of them. That's fine. Now this you can do this as well. Oh, sorry. Okay, weights also. So this is the logit that I have got. Okay. Okay. So what here I am doing is converting all the objects to data so that we can multiply and everything. Okay. So this can wait a bit. So I do that. It's already released, right? No need to for this. Microcrad, I do that. Microcrad, microcrad. So this all gets converted to okay, microcrad value. W microcrad, we can do it. W is let's do that. Let's do this. Let's do this. Let's microcrad. This also works, okay. Just putting that into establishing it up. So we have the input and this now we'll do logic. Okay, so we'll take this and the weight as well will take, and this will be microcrad. This is what we get here. And for each of the element, we do an exponent, okay? Okay, that's it. Microcrad, microcrad probability, microcrad. Micrograph, micrograph. That is summation now. Okay, it says chat micrograph has become data of data. Okay. Dot product, I'm going through two variables. So dot we are doing list. That needs to change, right? That multiplication I need to store. I to do this thing. Now when I do a dot, still I'm getting data of data. Okay, so I'm storing value rather than the there's the problem. This is fine, I believe. No, this is not fine. XSMG. So it is a list. No problem with this individual here. We're converting to tensor, doing a one hot encoder, and then doing a two float, then doing a two less. So again, let's go with this and this. Okay, so this is a list, nothing of a value or something coming, okay? No, it's fine. Okay, I'm not sure what was the issue. Can do this as well. I don't know. Mm, Let's do value variable. Again, pretty sorry for so many, but just to keep everything a bit sane and everything. So just check how it is. Getting it right. Again, if you run, then it might be a problem. W is again a data. W is again. What this does is it does. Okay, now it's okay. So if you run it again, that's not the problem because then value of value it becomes, so it creates a. Now we are going to call. Okay. Now we have nice values. Okay. Probability. So first we calculate the probabilities. Okay. Then what we do is we exponentiate that. Okay. Okay, sorry. This is just the sum, right? I think, yeah, okay. This is calculation and what's that then? Sum is fine. Okay. What got calculated here? We can again do it. So done. Ah, okay. So, now what I'm doing is I'm calculating negative log each. And this is the total count that comes, but I also want to do a differentiation, division. Should be by the number, right? I have that. I mean, sorry, average sum micrograd is equal to sum divided by number. I Oh, sorry. No, that was not supposed to be it here. Divided by 67, so 3 something like that. Okay. There's Now we do a back propagation of this individual. So all the weights would have been now interesting thing is we want to change the so all the micrograd weights that are there, right? No need for doing that. This is the one, okay. And for each of these weights, we'll have a gradient as well. So what we can do is it used to get us all the list for that, but it is not required itself actually. Get tree used to return all those, but that is not required itself. So what we'll do for all the WMG that we have, right? Each WMG Sorry. WMG. Weight microgram. Weight microgram. So this is a 17 by 17 cross matrix. By the 17, 17. Oh, okay, yeah, got it. Got it, got it. And I comma len, right? This is where I'm changing the values. J in this individual here. Really not sure why I'm WMG I comma J. I will take the gradient of that and sorry, the same thing I will do here. WMG I comma J. So for all the data that is there in the weights, right, I will fix it using and object is not iteratable. Oh, sorry. I should know to learn code well in Python as well, I believe. Okay. So weights are all now. The weights have been changed. So we'll do the dot product again. We'll calculate the probabilities, the sum. It's 3.25. Did it change? Not sure. Sum dot backward happen. Let's make it a bit more, not just say, okay. Sorry, yeah, 16, then 17. I do a backward, then I do a logit, then I do exponential, then I do this, and I do this, and I write the same. Just want to calculate, okay, how much it comes. It's reducing, but the yeah, it's pretty less. Okay, leave it. I will do a backward again. Here I will change it with say 50. Okay, it got changed here. Then I'm again doing taking the weights, exponential sum, and same values. It should reduce by. I'll say it reduced, say 0.23. What we can do then, no? I will put all of this in one function, right? Give me 1 minute. So I'll put all of these in one single this thing and iterate over it, okay? So anyway, dot is fine, encoding and all is fine. I think till this point it is all fine. We can take of this and loop around it. Say initial, right? Let's do it for just one. So this is the logic that we were calculating. Then we are doing exponentiation of this. Okay. Exponentiation is also done. Then we are calculating sum for each. So this is the same as, so we have, sorry, sorry. So this exponentiation, what we are doing. So this is forward for me. I'm using the same microgrid code that I wrote, right? And using that, I'm trying to run this. So this is forward. So I will, one is forward. Then for forward, the exponentiation is happening. Leave that, and this will be probability I'm calculating. Probability I'm calculating. So first is the sum for that, and then I will divide it. Okay. Where is this probability? MG is defined as well. There, okay, okay. Now I have the probability of each. I calculated exponentiation. Then I calculated the probability, and then I'm calculating the loss here. Okay. So these are all part of the second was the probability. The third is what I'm calculating. Loss, sorry, the average loss I can say. So that's average loss. This is where it is. Again, this is something is calculated. That's average loss for me. So that is forward. So I calculated the loss. Then I do a back propagation here. So this is 2, okay. Back propagate. I am doing a back propagate, and then I'm doing is changing gradient descent is what I think. No, changing the data using gradients. Okay, and that's what is happening here. Okay. And we loop it over. Okay. Looks fine. So if I run it again, 3.24. Sorry. 3.23. 305. So let me do it in say 10 iterations I want to run. I will remove this piece of code, which is a bit complicated anyway. For the time being, 3.21 is something that I caught. Okay, so the whole of this thing that I can remove random encoding and from here, right? It's all put in it there, backward this thing, that thing. Okay. So initialization, value and weights and everything is okay. That is all done. Neural nets, what I was trying specifically that I got the errors and then I can do prediction based on it, right? What should be it? Um, what is that probability looks like? So it should be something like probability ng. Probability mg is something that's coming in here. Not less. Ah, okay. So problem is that, sorry, this is the data type. One thing I wanna say. I'm just converting it to object now. Non-data type. It's non this sort of a data. Oh, screw it. Um, um, uh, In what way that can be different than this individual here? Oh, okay. I think it's the same thing. No, that I ran like multiple times. So this was using microcrad. We saw error reducing. Oh, we can run it a bit more. I don't know, like 50 more times. See, the error reducing again, the pace is slow, but this is what we get. Uh, could yes, these are much better models than that. Let's close it for this time. So first method was Andrej showed us just calculating the count and taking the probabilities and doing it completely easy. Here we are initializing the weight vectors or the probability vectors with something, and then using neural networks we are trying to reach the best probability matrix, where the error minimum we got was 1.32. Here it was 1.21. Still it's the best. Pretty simple. And then in the microcrad, right, using the same, there's nothing different. As of now, the minimum error that we reached was 3.16, which is way more, twice, thrice of what we are getting there. But I think if we run more times, we'll see reduction in the loss. And this is the prediction that's happening. So next we'll see, we'll go through the last part of this video, the next iteration, and see what all things we need to take into account or need to learn here. Okay. Thanks everyone. Thanks everyone.